especially for the possibility to give a talk about the stability and resilience in early morning after the gala dinner. I will speak about stability and resilience of organic matter pools in soil and their function by land use in Asia. And when we are speaking about the stability and resilience, we usually speak about groups of the qualities, groups of properties, physical qualities, chemical qualities, and also biological qualities. And our group work a lot with soil organic carbon because organic carbon join these qualities and is one of the main factors responsible for the physical, chemical, and biological qualities. And when this is present, we are very frequently speaking about the soil fertility, which is some kind of the summarizing parameter of the good soil properties. However, soil fertility can be destroyed very fast by intensive or very intensive land use, and it's coming to soil degradation. When we are speaking a lot about soil degradation, but what is behind it? I say there are, depending on the people who are doing the investigation, it could be very different things. Pollution, it could be contamination and others. However, I think in the most cases, there are two most important processes. This is erosion and soil organic matter mineralization, again because both of these processes lead to decrease of the organic matter pools and consequently has effect on biological, chemical, and physical qualities. I think the soil degradation is especially intensive in Southeast Asia because we should think about the main factors of soil formation. There are many soils in Southeast Asia which have parent materials clays. It means water penetration is not very good and the erosion will be accelerated. The climate is heavy monsoon rains and high temperature monsoon rains contributing to the high erosion. High temperature to mineralization of soil organic matter. There are very frequently, especially in the last decades, plantations. Relief is very hilly, contributing again mainly to the intensive erosion. And these soils are very old. Additionally, they are under very intensive land use. You can ask why Yakov invited me especially to speak about Southeast Asia, because I am actually from more or less Europe or even West Europe. However, our group worked in many parts of the hotspots of land use changes. Asia, we investigated in Tibet carbon and nitrogen pools under intensive grazing for many years. We investigated decomposition of very carbon-rich soils, molly soils, worked to paddy soils in the southeast of China, and to nitrogen use efficiency together with Yakov here in South Korea and also on the border between Kazakhstan and Russia. Investigated competition between various plants and between plants and microorganisms for nitrogen. Investigated also phosphorus pools by land use changes in Nepal, carbon input by various plants, and last but not least also formation of calcium carbonate in the dry area of the northwest of China. And this is probably just a small half of the topics which we investigated in the last 1 or 2 decades in Southeast Asia. However, today I would like to bring you a little bit more closer to equator, to Indonesia. Indonesia is one of the biggest hotspots of land use changes, and originally Indonesia was covered nearly completely by a very nice rainforest, tropical rainforest, which has the highest, one of the highest biodiversity in the world. However, in the last about 15-20 years, it is ongoing very intensive deforestation larger than in the whole Brazil, mainly driven by oil palm plantations and rubber plantations, which are economically much more efficient compared to other locations. And we investigated the consequences of transformation between a rainforest to oil palm plantation and rubber plantations in one of the few places remaining with the rainforest in national park, Hana. We made the soil profiles, investigated the soil depths, various soil properties, and at first surely again description of this is one of the typical clay soils, very highly weathered, very acidic soils in this area. And one of the first parameter, because I already mentioned carbon is important, we investigated organic carbon in soil. And you can recognize that in this part of the soil profile in this depth, the soils are very similar. However, there are the largest differences in the topsoil. And it was the question how we can investigate the decrease of carbon stocks by these two processes, erosion and decomposition, how we can disentangle this. For this we suggested completely new methods based on the isotopic composition of the carbon content in soil. At first, few words about our suggestion and hypothesis. If this is a carbon content and this is soil depth, this is common view for the carbon content, and erosion going from the top, and this is a mass flow. Mass flow doesn't lead to the changes of isotopic composition. The second process is the decomposition, which is ongoing very slowly. This is microbial process leading to the changes of increase of isotopic composition of the remaining soil organic matter after this tour. And we thought that if we will measure the isotopic composition of the remaining carbon, then maybe we can disentangle these two processes of soil organic matter destruction. So again, here I present the carbon content with depth, and you recognize easily that the most differences are in the top, and with depth they look very similar. However, if you look on the isotopic composition, this is presented natural isotopic composition of carbon-13 with depth, you can recognize that rainforest is very different from the plantations. And our idea was if we just move one curve against the other to the best correspondence, then we can assess the depth of the soil erosion. So we assessed 20 centimeters. What are 20 centimeters? We know that the plantation were about 17 years old, 17. It means erosion is ongoing more than 1 centimeter per year. And this corresponds roughly, probably more to 120, 150 megagram tons per hectare. It means every year about 10 big trucks soils will be removed from area. This is related to erosion. Then we have tried to investigate this process a little bit deeper and decided to make a phase diagram. Phase diagram means we related carbon content to its isotopic composition without the soil. And these are actually the various common forms. The top horizon, this is for the subsoil. And it is an interesting approach that actually if we take logarithms of carbon content to its isotopic composition, for all natural soils we have very good straight line, and the maximum carbon content is located actually here at the bottom part of the carbon content. However, if you look on the, for example, oil palm plantation, we see that the subsoil can make such a line, but the topsoil RH horizon is located not more consistent. And actually, because of our hypothesis that erosion have no changes for isotopic composition, we can move this location of the RH horizon and assess that the erosion contribute to about 2.5% losses. If you look on the rubber plantations, however, we see another situation. Again, this is a straight regression line based on this subsoil content and isotopic composition. And theoretically, the soil organic matter content should be sampled here. However, it's located here. It means during the degradation, isotopic composition changed by about this way. Consequently, we can conclude that in oil pipes, the erosion is the most important process. And in the rubber plantations, decomposition is the most important process. However, I think the most important was that we suggested completely new approach to disentangle two main key processes based on the isotopic composition of the remaining data sets in C. Now I have spoken just about the carbon, but there are many other parameters which are related to carbon, which are related to chemistry, biology, and so physics. And actually we decided to use another approach to investigate sensitivity and residence of soil fertility. We took organic carbon as the main parameter, again because it is responsible for physics, chemistry, and soil biology. And so that at first we can standardize it for the natural forest as the maximal value. And then we can see for the degradation. And this degradation corresponds to the decrease of soil organic carbon. We have also the second option to compare this degradation with various indicators. It could be microbial biomass composition, it could be phosphorus, nitrogen content, and other. Again, maximal value in the rainforest and minimal by the degradation. It means more or less the degradation curve look like this one between soil organic carbon and some of the indicators. If one indicator go faster than the soil organic carbon, than this line, it means this indicator is sensitive for the decomposition, for the degradation. If another indicator goes more slowly than the soil organic carbon, then this is a resistant indicator. If they are going a straight line, they are independent of carbon. If they are going by such a line, they are dependent on the soil organic carbon. This is again in the theory. Let us look now a little bit for the real data. Again, this is soil organic carbon. And these are various indicators: phosphorus content, nitrogen content, dissolved organic carbon, light fraction of organic carbon. And if you look, these are actually the sensitive indicators, and these are the resistant. If you look on the data, dissolved organic carbon and light fractions in this area, they are sensitive, especially sensitive. Correspondingly, if we are looking for degradation, we can recognize early degradation based on this parameter. The other parameters, like for example nitrogen or phosphorus content, they will be resistant. Probably in this case, because of the fertilization by the farmers. Very similar situation here with some microbial parameters, microbial biomass content, basal respiration, and activity of phosphatase, but they are not so strongly different. To increase these differences, we related again this parameter to the basal respiration on the similar way. Here is, in this case, basal respiration, and here are various indicators: nitrogen content, dissolved organic carbon, light fraction, and phosphorus. You can recognize again because it's changed the direction. These are sensitive parameters. Again, the same dissolved organic carbon and light fraction. And these are more resistant parameters. So we have developed one approach to assess the sensitivity and resistance of the parameters and various soil properties. And actually we can summarize this also as the other way to present the soil fertility maybe better. We can put standardized individual parameters: soil organic carbon, basal respiration, microbial biomass content, activity of some enzymes, phosphatase, light fraction, dissolved organic carbon, nitrogen and phosphorus content in such a diagram, and in which again each of them for rainforest is standardized with one, and then we can look for the shrinking of the area based on individual land use. For example, jungle rubber, this is more or less semi-natural land use, rubber or oil palm plantation. You can easily recognize by this diagram how strongly the area is shrinking, and and you can easily recognize that actually this is more or less the decreasing soil fertility, which is the highest in the rainforest and minimal in the oil palm plantations based on this yellow color. So we can also conclude from such a visualization that there are some parameters which are especially sensitive, which are decreasing the most strongly. There are some other parameters which are more or less resistant to the degradation. I am coming to conclusions, and there are two main processes of the soil degradation which are typically worldwide. This is erosion and soil organic matter decomposition. I think we can disentangle them by the isotopic composition of the remaining soil organic carbon based on the discounted sea values compared to the regional control. These two processes are especially intensive in Asia. We have tried to show that in oil palm plantation, every year more than 1 centimeter soil, it means more than 100 tons soil per hectare, will be lost. And rubber plantations have both erosion and decomposition. Oil palm plantations mainly erosion because it's very fast. We evaluated various indicators, soil parameters, based on the degradability, sensitive and resistant. Sensitive are dissolved organic carbon, light fractions, and activity of some enzymes, for example, phosphatase. Resistance are microbial biomass and basal CO2 respiration. And again, we suggested another new approach to evaluate sensitivity and resistance based on the comparison to the soil organic carbon. We estimated the soil fertility indicator actually by the shrinking of the area of various parameters. And last but not least, but such approach consider both physics, chemistry, and biology of soils, considering the soil organic carbon as the main factor. And some of these results were recently published in Nature Communication, and I would like to thank you and the German Science Foundation for the funding. Thank you.
Thank you very much, Yakov. And running to time. Time for a couple of questions. Do you have anything you'd like to ask?
Good morning. Any questions?
It's a great presentation. I love it. Thank you for that. My question in relation to erosion. You have used C13 to disentangle between the soil erosion and decomposition.
Yes.
In most of the erosion work, they have been using cesium isotope.
Mm-hmm.
Did you have a look at that, whether you could use that, disentangle between,
Yes.
I know the purpose of cesium is more into erosion total loss, soil loss, not carbon loss. But if you look at cesium with some enrichment factors, whether you can
This is a very good approach to measure erosion based on cesium-137 or strontium-19 or some other isotopes. But this approach works very well in the area which were not very far from the atom bomb tests. This is one point. Most of them were in the northern hemisphere, not on the equator, not close to Indonesia. This approach works well if the erosion is not too strong. If the erosion is too strong in the last 60 years, then the top layer in which the cesium will be, in which fallout will be accumulated, if it will be removed, it's too late. And this is especially the case also in Indonesia. So we did not use this approach just because, first, it is very far and it is good for the atom bomb locations. And secondly, because the erosion is too strong to measure, because 1 centimeter per year, this is too much. Okay?
Thank you.
You're welcome.
So I have a final question for you. So these erosion rates are enormous.
Yes.
The amount of material that's been eroded from 48 to 120 megagrams per hectare per year. So I'm wondering, on a spatial context across Indonesia, if you multiply up the carbon content of that eroded soil, what the carbon losses are.
It surely is useful for nature for globalization on the local context. And so we have not done, I'm not working with geo information systems, so we have not done this, but it's surely possible, and this would be huge locations, especially considering the nearly all area covered by plantations. Yes, by plantations. But again, this is 150 megagram, and this is about 10 times more than it's allowed in Europe, despite what is allowed in Europe, about 10 times more than the natural soil formation rates. And consequently, this is about maybe 100 times faster than the natural soil formation.
Understood. Thank you very much.
Thank you.
On the